Section 3.6 is about the derivatives of log functions. So we're going to start out by trying to find the derivative of the natural log function. Now here's a situation where I know if y is equal to the natural log of x, that function is the inverse of y equals e to the x. The log function with base e is the inverse of the exponential function with base e. Now, what that means is that this equation right here is equivalent to just taking this equation and switching the roles of x and y. So y equals the natural log of x means x equals e to the y. This is actually very similar to what we had with inverse trig. At the start of the last section, we didn't yet know the derivatives of the inverse trig functions. But we knew that they had a very important relationship to the trig functions. If we restricted the domains appropriately, then they were just the inverses of those functions. Here, we don't need to restrict the domain. This is the inverse of this function, and I know the derivative of e to the x. So I'm going to be able to take advantage of the fact that I can rewrite this function by just switching the roles of x and y in my exponential function. I'm going to find the derivative by using implicit differentiation. So I'm going to say the derivative of x is equal to the derivative with respect to x of e to the y. Derivative of x is just 1. Derivative of e to the y is e to the y times y prime. Now I solve for y prime and I get that it's 1 over e to the y. But e to the y was just a fancy name of writing x. Okay. Just like with the inverse trig functions, because we actually do explicitly know the relationship between x and y, we don't have to stop with having y's in our formulas. We can go ahead and replace that e to the y with x. So the derivative of the natural log function is the reciprocal function. Derivative of the natural log of x is 1 over x. Now, one thing I should mention here. It is understood when we're taking the derivative that the domain of the derivative has to be some subset, possibly the whole thing, of the domain of the original function. For the natural log of x, the domain is only positive numbers from 0 to infinity. Now, the function 1 over x, if I'm just looking at it in its own right, not as being the derivative of the natural log function, that has as its domain everything from negative infinity to 0, union from 0 to infinity. So if I take a look, here's my natural log function. Sorry, y equals the natural log of x. Its derivative would be y equals 1 over x, but only the part where x is bigger than 0. I can't have a derivative over here if there's nothing for it to be the derivative of. Okay? But I know that 1 over x in its own right is defined for negative values as well. So it would be kind of nice if we could find a function that agrees with the natural log of x for positive numbers, so that its derivative here will be 1 over x, but that's defined for negative numbers and has as its derivative 1 over x when x happens to be a negative number. And it turns out that we can. Okay. So we've got this formula that the derivative of the natural log of x is 1 over x. That is true, and it's understood that this is only the derivative if this function is defined. Okay. I'm going to look at a related function. I'm going to let y equal the natural log of the absolute value of x. Okay, now I can write that as a piecewise function. because I know that if x is positive, the absolute value of x is just x. So this will be the natural log of x if x is positive. If x is 0, that's not in the domain of this function because I cannot take the natural log of 0. But if x is negative, taking the absolute value makes it positive so that I can plug it into the natural log function. And I know if x is negative, then I can replace the absolute value of x with the opposite of x. This is what we would get if x is less than 0. This is not representing a negative number. This is the opposite of x when x is a negative number. And the opposite of a negative number is positive. So I can write the natural log of the absolute value function piecewise, like so. Then I can take the derivative of the natural log of the absolute value function piecewise. If x is positive, it's just the natural log function. We just calculated that that derivative is the reciprocal function. Here, I've got a function composition. So I'm going to have to use chain rule. I've got the natural log evaluated at negative x. So when I take the derivative, I'll get the reciprocal of negative x times the derivative of negative x. That's what I get if x is less than 0. Okay. But the derivative of negative x is just negative 1. So I get 1 over x if x is positive. I get 1 over negative x times negative 1. And those negatives are going to cancel. So I actually just get 1 over x, and that's what I get if x is 0. So even though I had to write this function piecewise, I don't have to write its derivative piecewise. It is also true that the derivative of the natural log of the absolute value of x is just 1 over x. That's kind of remarkable. In general, if I start with a function and I take the absolute value of that function, I can expect that that's going to affect the value of the derivative. If I just take a line of slope 2, when I take the absolute value of that, it flips this negative piece up. So now the derivative is negative 2 over here, positive 2 over here, and undefined here. It's a very simple function where the absolute value drastically changes the derivative. Well, here, taking the absolute value does change the derivative as well. It just doesn't look like it does. What it does is it moves from this function only defined for positive values to this function also defined for negative values. Okay? So the domain of this function and the domain of this function are different. Natural log of x is only defined for positive numbers. Natural log of the absolute value of x is defined for any non-zero number. The formulas for their derivatives are the same, but I'm only going to use this formula if I can use this function if x is positive, whereas here x can be either positive or negative. Okay. As we're taking derivatives, we're mostly going to be working with this at first, but we're going to see it's often very, very helpful to know that if I take the derivative of the natural log of the absolute value of something, even though this is a function composition, I'm plugging the absolute value function into the natural log function, I don't have to, because I've done it already, I don't have to write that out as a function composition and use the chain rule. I can just jump to it's the reciprocal function. I've done the work here. Now I can add this to my list of known formulas.